We begin tackling dynamic collision detection by explaining how to detect collision between a line segment and a capsule and capsules with each other. A line segment is the subsection of a line or array. It is defined by 2 points, one for its start point and one for its end point. A capsule represents the swept volume of a sphere between two update frames, the current and the previous. Between the frames, the sweep is linear, so a capsule is just a line segment with a radius. Collision detection between a line segment and capsule is fundamental for detecting dynamic collision between two spheres and a sphere and a bounding box. To detect whether a line segment and a capsule are intersecting, we define a line segment using the start and end points of the capsule. Then we find the closest points on the line segments to each other. We then test whether those points are within the square radius of the capsule. If they are, there is collision. We use the square radius rather than just the radius to avoid the expensive square root function. To summarize the closest points on the line segments function, we first find the closest points on the infinite lines that subsume the line segments. We then clamp these points to the bounds of the segments to get our final result. To make this robust, we check for degenerate cases first. This occurs when one or both segments have near zero length, which implies the collision primitives are static between frames. In the argument list, we take in two line segments and write out to the parameters along segments the closest points correspond to. These parameters are between 0 and 1 when they are within the segments, and below 0 or above 1 when they are outside of the segments. We also write out to the closest 2 points. We first create vectors between the segment start and end points. We use these vectors to get the square lengths of the segments, which allows us to have values that are proportional to the length of the segments whilst avoiding the square root function. The first conditional tests whether both segments have degenerated into zero-length points. If so, the parameter along each segment would be 0, and the closest points would be both the start and end points, since they have the same position. Because this function returns the square of the distance, we perform a dot product on the difference between the two closest points. We calculate a gap vector between the segment's endpoints. We then use it to calculate its projection onto segment 2, the purpose of which will be explained soon. The next conditional checks if just segment 1 is degenerate. In this case, the parameter along segment 1 would be 0. Because segment 1 is just a point, finding the closest point to it along segment 2 is simplified. We divide the projection of segment 2 onto the gap vector by the square length of segment 2. The projection gets us how far along segment 2 we need to go to find the closest point, but it's in square units because we use the dot product to produce it. We divide by the square length of segment 2 to convert to linear units. This value might be on the infinite line that has the same position as the line segment, but extends past its demarcation points. We clamp between 0 and 1 to ensure it is within the bounds of the segment. By the next conditional, we have confirmed that neither of the line segments are degenerate. When both segments have real length, the geometry involves two directions, two scales, and a shared area between them. To solve for this, we need to solve for a system of linear equations. This leads us directly to a powerful geometric tool, the Gram determinant. To understand it, we need to start with the basics. A linear equation is an algebraic equation where the highest power of a term is 1. A number to the power of 1 is itself, so it's not usually made explicit. On a graph, a linear equation forms a straight line, as opposed to a curved line for nonlinear equations, such as quadratics. A system of linear equations involves two or more linear equations. A square matrix has the same number of columns and rows. The determinant of a square matrix is a scalar value defined by the formula A times D minus B times C. It tells us if a unique solution to a system of linear equations exists. The unique solution is the point of intersection between the lines and indicates the determinant is not zero. Keep in mind, the lines intersecting does not necessarily mean the line segments are intersecting. A zero determinant result means the system either has infinite solutions, meaning the lines are overlapping and thus intersect at an infinite number of points along their span, or, alternatively, there is no overlap and the lines are just parallel. Geometrically, the determinant represents the signed area of the parallelogram formed by the matrix's column vectors, so it can be positive or negative. Each component of a 3D cross product is itself a 2x2 determinant. The cross product calculates the vector that is perpendicular to two vectors. The vector connecting the two closest points on two infinite lines is always perpendicular to both lines. However, this is not necessarily true for line segments. For two-dimensional vectors, the cross product forms a vector that exists outside the two-dimensional plane. The x and y components of this vector are 0, so its z component is treated as a solitary scalar, which is why our determinant is stored in a single float. The magnitude of this z component is equal to the area of the parallelogram. A gram matrix's elements are composed of the dot products between a set of vectors. The gram determinant is the determinant of a gram matrix. Because the diagonals of its elements are self-dot products, which are always non-negative, the resulting determinant is always non-negative for a 2x2 gram matrix. The gram determinant of a 2x2 matrix is correlated with the trigonometric operation sign, so if the vectors are parallel, the gram determinant will be 0. If the line segments were perpendicular, the sign would be 1. Correspondingly, the gram determinant will yield a positive value, scaled by the square lengths of the segments. To find the values along the segments, we will divide the area representing the closest points by the area representing the two segment vectors. This will give us the value in linear units. The area representing the closest points can be larger than the area representing the two segment vectors, because the closest points can be beyond the demarcation points of the segments. As we look at the variables in our gram determinant, we see that the first product simply multiplies the square length of the first segment by the square length of the second. This would give us the area of the parallelogram, but would be insufficient by itself because parallel segments should yield 0, remembering that it correlates with sine. By subtracting the projections of the segments onto each other, and thus what is directionally similar, we remove the parallel contribution, leaving just the perpendicular component. Now that we know the area represented by the determinant, how do we isolate the part that corresponds to just one segment? That's where cofactors come in. They're like taking a snapshot of one segment's contribution to the overall geometry. Another name for the cofactor is the minor determinant. It is the determinant of a submatrix. This submatrix is usually formed by deleting the row and column of a matrix that intersects an element and then performing an operation on the remaining elements. Under Cramer's rule, we solve for the unknowns, which are the parameters along each segment in our case, by replacing columns of the coefficient matrix, the gram matrix in our example, with a right-hand side vector. The right-hand side vector is a column containing the values from the equations our unknowns must satisfy. In our system, the right-hand vector is comprised of the projections of the gap vector onto each infinite line. Replacing the first column with the right-hand side vector and calculating the determinant of this matrix gives us the parameter along segment 1, while replacing the second column gives us the parameter along segment 2. The gap vector serves as a basis vector for projection onto the infinite line that contains the line segments. There is nothing inherently special about it. We could use any vector as long as we use it consistently. The projection of the gap vector onto each segment vector represents a portion of the total area of the parallelogram defined by the two segments. This area correlates with the length of the gap, so it can exceed the area of the parallelogram when the gap is long. It scales in proportion to the perpendicularity of the line segments, just as the gram determinant does. By replacing segment 1's square length in the first product with the projection of the gap vector onto segment 1 and replacing the alignment of segments in the second product with the projection of the gap onto segment 2, and then subtracting the results, we obtain the area representing the closest point in relation to the area representing the lengths of the segments. Once we divide the cofactor by the determinant, we have a linear value, which is the parameter along the infinite line relative to the segment that coincides with the closest point on line 1 to line 2. Once we clamp to the segment's limits, we have the parameter along the line segment that corresponds to the closest point. If the gram determinant was 0, which means the segments are parallel, we set the parameter along segment 1 to 0 as a basis to calculate the parameter along segment 2. Since we have the parameter along segment 1, we can compute the parameter of the closest point along segment 2 using fewer steps. We multiply the parameter along segment 1 by the alignment of the segments to translate how much it projects onto segment 2. We then add the projection of the gap vector onto segment 2 to account for the offset between the segments along segment 2's direction. Now we have the total value in square units. Finally, we divide by the squared length of segment 2 to convert the projection from square units into a linear parameter along segment 2. In this example, with the segments being perpendicular, the alignment is 0, which leads to the parameter along segment 1 equating to 0. The parameter along segment 2 ends up being minus 0.5. 0 times 0, add minus 1 divided by 2. You can see that it puts us where the infinite lines would be intersecting. If the gap vector was larger, the intersection point would be further away, because the value is scaled exactly by that. Since the parameter along segment 2 is less than 0, we set it to 0 to keep it within the segment's range. We set parameter 1 to the projection of the gap vector onto segment 1 scaled back into linear units with the division, then clamped within the extrema of the segment. This is almost exactly what we did when the parameter along segment 1 was 0 earlier in the function. We negate the projection because we define the gap vector pointing towards segment 1's endpoint rather than segment 2's endpoint. So we need to flip the direction when projecting onto segment 1. The alignment of the segments is not in this operation, because segment 2 is being treated as a point, so it's irrelevant. If the parameter along segment 2 is more than 1, we set it to 1 to land at the end of the segment. We subtract the projection of the gap vector from the alignment of the segments to get the corresponding parameter along segment 1 that lines up with the closest point on segment 2. We divide it by the square length of the segment to convert it into linear units as usual. At the end of the function, we calculate the closest points by adding the segment vectors multiplied by the parameters to the segment's endpoints. We then return the square of the vector between the closest points, so the calling function can test for collision. The capsule and capsule collision function is very similar. We just add the radii together before checking if it's less than equal to the distance. I'll be extending this material into a structured course on Gumroad that covers more dynamic collisions and my overall system architecture. I'll share details when it's available. Thanks for watching.